presentation. I think a really important point to make is that the deep sea is not a single ecosystem. Over the past 50 years, we've evolved a great amount of technology that's allowed us to explore the deep ocean, and this has revealed a wealth of environmental heterogeneity. We have sonar for mapping the seafloor and acoustic tools for looking at gas bubbles and fish. We have submarines and remotely operated vehicles and camera sleds and autonomous underwater vehicles. And these have all revealed that rather than being a flat, monotonous, and desert-like environment, which we once thought, there is, in fact, a wealth of environmental heterogeneity. There are many different ecosystems in the deep sea, and each of these has their own biodiversity and their own resources. So we have discovered that there, beneath upwelling areas, there are regions of very low oxygen. As Bijoy said, I've been studying these for many years. In our low productivity areas, the seafloor are vast abyssal plains. We have tens of thousands of seamounts or underwater volcanoes covered with lush gardens of animals, corals, and sponges. We have thousands of canyons that cut our continental margins, also with coral and sponge gardens. We've discovered these animals, the corals and sponges, can form vast reefs that extend for many kilometers and support a wealth of biodiversity. And we've discovered there are chemosynthetic ecosystems, both methane seeps and hydrothermal vents, whose animals live off chemoautotrophic bacteria. That is, they get their energy from chemicals emerging from the seafloor rather than from sunlight and photosynthesis. And then we have the most vast area, the deep pelagic realm, also really relatively undiscovered. And we found that each of these ecosystems, in addition to having a tremendous amount of biodiversity specialized to that system, each has its own resources that are increasingly of interest to people. So in oxygen minima, there are phosphorite minerals of interest for use as fertilizer. In abyssal plains, there are polymetallic nodules rich in copper, zinc, cobalt, and nickel that are of interest for mining. The seamounts are covered with crusts that are also metal rich in copper, nickel, molybdenum, and cerium of interest for mining. And the hydrothermal vents precipitate massive sulfides rich in copper, zinc, lead, silver, and gold, again of interest for mining. We've discovered that the canyons accumulate vast amounts of organic matter that turn into oil and gas over time, and now we are beginning to extract that. The seamounts are sites of tremendous aggregations of fish, such as the orange roughy you see here, and we've begun fishing these. Fish also hang out at methane seeps like the Chilean sea bass, and fish are nurtured in the cold water coral reefs. And so humans have begun to exploit the resources in the deep sea. They're even looking at the billions and billions of small mesopelagic fish that migrate up and down, myctophids, for example, as a new fishery in some places. Despite the fact that we've learned a great deal about the deep sea, we are still, I think, in an era of discovery. We've mapped less than 20% of the seafloor, and I think we've really studied less than 5% of it in any detail with respect to the biology. So we are discovering, for example, new ways of living. Here on the Costa Rica margin, you can see a wall, literally a wall of worms, serpulids and sabellids that we once thought were filter feeding animals. Turns out these worms on the Costa Rica margin are farming methane oxidizing bacteria in their tentacles. So those bacteria live symbiotically and are using methane as a food source to feed these worms. We've discovered also off Costa Rica some strange crabs, these dancing yeti crabs, which are farming bacteria on their claws. They wave them, provide the sulfide and methane, access to sulfide and methane that the bacteria use to fix carbon, and then you can see the animals will eat these bacteria as a food source. We continue to discover that deep sea ecosystems provide nurseries in new ways. We've discovered sponges are nursery habitat for juvenile rockfish, that fields of sea pens are nursery habitat for fish larvae that live inside and amongst their stinging tentacles. We've discovered that masses of octopus brood their young at warm seeps, at warm venting from seamounts. We've discovered that hydrothermal vents and methane seeps can function as nursery grounds for skate and ray egg cases. We found that deep sea corals host masses of tiny little crustaceans, and this is my favorite and most recent discovery from off Costa Rica. We found that giant agglutinated protozoans called xenophyophores provide nursery habitat for snailfish embryos. We are discovering new connections. The carbonate rocks precipitated by microbes at methane seeps, for example, host a variety of different animals and all the bacteria that live on and with these animals. And we've learned that other species like the octopus, rays, and crab you see here come from outside the seep ecosystem to forage at the methane seep and take the chemosynthetic energy away back into the rest of the deep sea. We continue to discover new ecosystems in the deep sea. This hydrothermal seep was discovered at 1,850 meters off Costa Rica. This is a place where a subducting seamount is venting warm waters on an organic rich margin, which has basically a lot of methane. And so we have hydrothermal vent animals co-occurring at the same site as methane seep animals. We've learned that the animals that adapt to live in these extreme environments in the deep sea have superpowers. And so the animals that can tolerate the warmest known temperatures on the planet, like these worms at hydrothermal vents, are found at Juan de Fuca. We found animals that can tolerate the highest levels of hydrogen sulfide, which is normally toxic, at methane seeps. We find animals that can tolerate the highest pressures, 800 times more than what you and I are living at. We find animals that can live in practically no oxygen in some of our oxygen minimum zones, and animals that can calcify and make their skeletons at very, very low pHs. There are other kinds of superpowers that come from symbiotic bacteria. We find mollusks that can digest wood, and we find worms that can digest whale bones. But my favorite superpower in the deep sea is that of extreme longevity. There, the fish typically live for more than 100 years, sometimes 150 years. These are all commercially harvested species that once harvested won't recover very quickly. But there are longer lived species. There are sharks that can live for hundreds of years, and tube worms at methane seeps that can live for hundreds of years. But even these are very young compared to some of the deep sea corals and sponges that can live for literally thousands of years. And this great longevity means that the animals grow very slowly, and they also recover slowly from disturbance. Now, these environments, even though we are continuing to make all these discoveries every year, are not pristine. There is a growing human presence in the deep sea, and this comes from growing population. When I was 5 years old, there were 3 billion people on this planet, and there are now more than 7.5 billion people. And this tremendous increase in population has led to a demand for more food and for more energy, for more raw materials, and recently for a variety of metals to fuel our electronics and our green technologies like hybrid cars and wind turbines and solar cells. And as we deplete resources on land, we look to the ocean for these materials and food. And as we deplete the shallow waters of the ocean, we look into the deep sea. Now, the deep sea used to be pristine, but technology has now enabled us to find any resources and reach anything we want and go as deep as we want. We have satellite guided GPS and very precise mapping tools. We have fishing gear that allows us to deep fish at any depth, infrastructure for oil and gas extraction at pretty much any depth, and now we're developing new tools for mining the deep seabed. I mentioned we can fish deep, and in fact, we have been fishing continuously deeper over time. It's now routine to fish below 1,000 meters. This is especially true in Antarctica, where fishing is getting deeper much more rapidly. And as we fish deeper and deeper, this leads to overfishing of slow-growing fish species. It leads to lost gear, which continue to capture fish. We call that ghost fishing. It leads to endangerment of fish species through bycatch. In fact, in the North Atlantic, there are many fish species that were never targeted, but now are endangered species because so much has been removed as untargeted bycatch. And also bottom fishing is disturbing the three-dimensional structures and leading to basically piles of rubble that you see here, where those coral and sponge structures often host the important biodiversity on the seafloor. I mentioned oil and gas is getting deeper continuously. Extraction, both, I should say, exploration and production are getting deeper over time. Nowhere is this more evident than in the Gulf of Mexico, which you see here off Texas and Louisiana. There are more than 5,000 oil rigs, and you can see that the biggest circles are the most recent of these, and they're all in very deep water. The most famous of these is the Deepwater Horizon, which blew out in 2010 and has led to tremendous amount of destruction of deep sea life. There are other kinds of concerns besides oil spills. There's noise and discharge of cuttings as well, but that oil spill was very massive. We've also, as I mentioned, discovered that the deep sea is a gold mine of minerals, and the international minerals are recognized by the law of the sea as the common heritage of mankind. There's interest in harvesting ferromanganese crusts on seamounts, and the International Seabed Authority has leases that are up to 3,000 square kilometers per contractor. There are massive sulfides at hydrothermal vents, and there are exploration contracts, 10,000 square kilometers in area. There are exploration contracts for polymetallic nodules in the abyssal plains. India has some of these, and these individual contract areas are 75,000 kilometers squared in area, so they're very massive. This is a map showing the international exploration contracts for deep seabed minerals, and you can see the countries in blue are the countries that actually have these international contracts, and I've circled the region where India's are here for polymetallic nodules and part of the Southwest Indian Ridge for massive sulfides as well. You can see there's a very large area. Well, let's see what my next slide is. I think I put this slide in to really illustrate that India's interest in mining minerals on the deep sea floor for their metals is growing. There's been a variety of articles, and India, as I said, has 2 lease areas from the International Seabed Authority, and just last year put out an environmental impact statement for testing a polymetallic nodule collector for its contract area in the Indian Ocean. Now, the area with the most interest is, in fact, the Clarion-Clipperton Zone off the coast of Mexico in the Eastern Pacific. And there are about 20 countries that have contracts in this region. They're surrounded by a zone of protected areas. But this is a really vast area. You can see if superimposed on the United States, it's about 3,000 miles across, I think. It's truly a huge area with many, many different exploration contracts, which are sort of on the verge of becoming exploitation contracts. And the scale of these contract areas, as I mentioned, is huge. Here I show the size of the very largest strip mine for coal in Germany, and a single year of mining polymetallic nodules in the Clarion-Clipperton Zone would cover several times that area. But to be viable, the mining operations have to last for 20 to 30 years. And so you can see that a single contract area, if mined, would cover many, many times the area of Germany's largest coal mine. And if you go back and look at how many different contract areas there are, this is a lot of seafloor that is now vulnerable to mining. Science tells us that mined areas may not recover in these nodule provinces very quickly. The animals grow and recover slowly. There was test dredging in the 1980s, and these sites have been visited 20 and 30 years later. The test mining scars are still sharp. There's been little recolonization. Even the microbes have not recovered fully after 20 to 30 years. And what this means is that mining of these environments probably will take centuries for recovery. So all of the extraction activities that I've been talking about bring different sorts of disturbance to the seafloor: physical disturbance, suspended sediment plumes, altered substrates, release of contaminants, sometimes metals, from the seafloor, loss of structure, and altered food webs. And while the direct human footprint is growing, the ocean is also changing as the result of carbon dioxide emissions, which is depicted here. These are warming the atmosphere. You see they come mostly from the northern hemisphere, but they affect the entire ocean. And the ocean is, in fact, our greatest climate mitigator. It absorbs 93% of the excess heat from those greenhouse gases. That leads to a warmer ocean, which means less solubility of gases and more stratification. And this leads to declines in oxygen in the ocean, what we call ocean deoxygenation. The stratification or increased density layering also reduces the vertical mixing of nutrients, and so there is reduced primary productivity in many parts of the ocean going on as well. The carbon dioxide, about a quarter of the excess CO2, is taken up by the ocean, and this leads to what we call ocean acidification. And all of these changes are happening in the surface waters of the ocean, but they do not stay there. Both the excess heat and CO2 are being transferred fairly rapidly into the deep ocean by thermohaline circulation and convection, what we call the Great Conveyor Belt. And this is leading to a warmer, more acidic, and less oxygenated deep ocean. And these changes in the deep ocean have consequences for deep sea life. They're redistributing species and changing migration pathways of species, such as the tuna and these deep Antarctic crabs. The warming has the potential to release more methane, which is buried on continental margins and is a very potent greenhouse gas. Loss of oxygen in the ocean is causing loss of reduced biodiversity, changes in food webs, and habitat compression of species like tuna, billfish, and sharks. And the increased acidification of ocean waters is threatening to dissolve at least the non-living parts of deep water coral reefs and making calcification much more difficult. I believe that climate change has, which is projected in these figures to the end of the century, will make recovery from human disturbances much more difficult. In these projections from Earth system models, we see all the areas in blue here are areas projected to have reduced POC flux, that is a reduced food supply to the seafloor, and less food will make it harder for animals disturbed by fishing, mining, or oil extraction to recover from disturbance. Most of the deep sea floor is projected to experience declines in pH, and these reductions and lower aragonite saturation states will slow coral recovery from disturbance. Much of the deep sea floor, the areas in blue, will have lower oxygen, which can cause a loss of species and exacerbated stress from sediment plumes. And most of the deep sea floor will be warmer than it is now. Rising temperatures increase metabolic demand, redistribute species, and their biogenic habitat that they produce. So we're in a place where we have climate change occurring at the same time that we have growing human disturbance in the forms of fishing, oil and gas extraction, mining, and even litter and debris. Well, why should we care about these threats to the deep sea? I would argue that the deep sea ecosystems are very much like rainforests of the deep. They host biodiversity with tremendous potential to benefit humankind. Beyond the wonder and beauty, there is biopharmaceutical potential. For example, in a variety of different sponges, there are secondary compounds in testing for cancer treatment as antibiotics or anti-inflammatories. And you know, we value our rainforests on land for all the natural products that they can produce to help people, but the deep sea is also has a wealth of these. And in fact, we can think of deep sea biodiversity as one of our ecosystem services. Beyond the new species that we're discovering, there's a wealth of genes, and they provide the ocean with the potential to adapt to to changes that we know are occurring. There are enzymes now employed as that can break down lipids as cold water detergents or can provide UV resistance. I mentioned there are metabolites with antibiotic, anti-cancer, and anti-inflammatory potential. There's an amphipod in the deepest Marianas Trench with a chemical very similar to one being used to treat Alzheimer's disease. There are biomaterials and biomimicry, sponge fibers being studied as optics, coral bones as coral as templates for bone grafts, and the armor in this scaly foot snails being looked at as a template for new forms of airplane hulls and car armors and so on. There are anti-fouling properties. There are detoxification properties. There are cellulases with interesting fermentation properties, pyrolases used in fracking. Deep sea tube worms at vents are providing a template for artificial human blood. There's UV-resistant skin products, and one of my favorite are some of the microbes at vents now being looked at for their ability to scrub CO2 and perhaps help solve our climate problems. The deep sea is vast and provides important regulating services, both nutrient cycling, which fuels primary productivity in surface waters, and also the sequestration of carbon over much of the seafloor, which has been valued at more than 125 billion per year in terms of its value. The deep sea also provides many different cultural services. It's been inspiration for film and literature and art. It's the source of space for our communication cables and, of course, for scientific research, which is ongoing, and even in some cases for tourism. So we have many reasons to want to take care of the deep ocean. What can we do to promote its sustainability? Take a break here. And I think to understand and answer this question, we have to know who owns the ocean. And we are told who owns the ocean from the UN Convention on the Law of the Sea, which went into force in 1992. So the Law of the Sea tells us that the 154 countries with coastlines own the ocean out to 200 nautical miles from shore. And they can also claim an extended continental shelf even further out. But the rest of the ocean, about 2/3 of it, is the international ocean, the area beyond national jurisdiction, which consists of the water column called the high seas and the seafloor called the area. And this is a map showing the jurisdictions of the ocean, and all of this area in tan, about 60% of it is international. And the international waters are governed in a very fragmented way by different United Nations agencies. And this is a diagram of what we call the alphabet soup of high seas and deep seas governance, with the organizations on the right side governing the use of the extractive use of resources. For example, the International Seabed Authority for International Minerals, the International Maritime Organization for Shipping, the FAO and RF, Regional Fisheries Management Organizations for the Fish, International Fish. The London Dumping Convention governs the litter and disposal of waste. The Whaling Commission governs the whales. Science is managed by the Intergovernmental Oceanographic Commission. And then on the left side, we have the more conservation and science-oriented agreements that manage migratory species and biological diversity and endangered species. We have the UN Framework Convention on Climate Change, which manages climate, and a new treaty being negotiated under the Law of the Sea on biodiversity beyond national jurisdiction. So there are all of these different organizations in charge of that 60% of the ocean in international waters. And all of these organizations need scientific information to function and make decisions and make policy. And there's a lot of policy being made right now about the deep ocean. So I would like to talk just some about how to bring deep sea science to policymakers. And to do this, I'd like to talk about the Deep Ocean Stewardship Initiative, whose mission is to integrate science, technology, policy, law, and economics to advise ecosystem-based management of resource use in the deep ocean and strategies to maintain the integrity of deep ocean ecosystems within and beyond national jurisdictions. And I'm just going to give you a bit of a personal flavor. I helped to found OSI in 2013, but the roots came in 2011 when I was on sabbatical with my husband in Namibia, a small country in southern Africa. And I came there to study their amazing low oxygen ecosystems. They have a very productive upwelling system, the Benguela system, with mats and leading to very productive fisheries, hake and horse mackerel fisheries that also fuel for seals and birds, and it's an amazing ecosystem. I was fortunate to be able to teach, go to sea there, and work with people. But towards the end of my stay, I was working at the Fisheries Ministry. They discovered that the Minerals Ministry had leased out for phosphate mining much of their deep water at 100, 200, 300 meters water depth. In fact, they had leased out their prime fishing grounds without even consulting the fishing ministry. And there had never been even a single scientific paper about what was living on the deep, on the seafloor where they had leased for phosphate mining. Phosphate, as I mentioned, is of interest for fertilizer. And I realized at that time that countries like Namibia had not a single deep sea biologist. There was no way for them to have really the information or even the governance and law and policy expertise to address this kind of decision making that needed to happen. And so I went, that's what the phosphorates look like. When I returned home to my university, I worked hard to get some grant money to hold a workshop that led to the development of the Deep Ocean Stewardship Initiative. We started with a workshop in Mexico City with 24 people, a mix of biologists and economists and policy and law and policy experts. And now DOSI has 1,800 members in 85 countries, working to advance deep sea science, inform policy, and particularly to enhance the capacity and collaborative abilities of countries around the world that are making decisions about their deep ocean. And there are 10 working groups in DOSI. So to give you some sense of how scientists can actually influence international policy making, I want to talk about the work that these different working groups are doing. The Fisheries Working Group is interested in habitat recovery, in understanding the relationship between natural variability and human impacts, managing the expectations of protected areas, and the effectiveness of impact assessments. Both the Fisheries and Climate Working Group teamed up with the FAO to do a report on deep ocean climate change impacts on habitat, fish, and fisheries. They have worked with the European Union to establish a deep sea trawl ban below 800 meters, and they're very active in the South Pacific Regional Fisheries Management Organization. DOSI has an oil and gas working group that has come together to synthesize the environmental impacts of the deep water oil and gas industry in this very nice review paper to guide management. It's producing sets of best practices recommendations for resource managers that can be applied both within and beyond national jurisdiction. And just recently, they reviewed an impact assessment for drilling off South Africa. There are major oil leasing areas, and in fact found so many shortcomings in the environmental impact statement that the government, in fact, halted drilling plans and is going to be doing further review. The biggest group in DOSI is the Minerals Working Group, and that group works with the International Seabed Authority. It sends a delegation, usually twice a year when the meetings are happening. It produces policy briefs to inform the delegates about deep sea science and environmental impacts. The group, very importantly, gathers expertise from all the science members and provides critique of the newly developed regulations, both the exploration and the draft exploitation regulations. It's done 4 iterations of these with critiques that will often bring together the input of 20 or 30 different people. And in fact, this Minerals Working Group just submitted some months ago, submitted a commentary on the environmental impact statement for a polymetallic nodule collector prototype issued by the government of India for its contract area. And if anybody is interested in seeing that critique, I'd be happy to share it, public information. DOSI is dedicated to building capacity of countries to make decisions about their deep sea areas. And just last October, we held a mini course for the West Pacific, South Pacific Islands nations called the Deep Sea Humans and Management. There are a series of 8 20-minute lectures that are in fact available to anybody on YouTube, with a tremendous amount of information that introduce the deep sea and its dynamics and functions, information about seabed mining and fishing and management, conservation, and so on. Turns out that not only is there interest in mining minerals from the seabed, but the waste from terrestrial mining is also being dumped into the deep sea down pipes. This is happening in 6 countries at 17 locations, and DOSI has a deep sea tailings disposal working group that has conducted several reviews of the environmental impacts of this disposal activity, and is also worked on a Papua New Guinea conservation environmental protection guidance, and is working to scale this up as a global best practices document. The DOSI Climate Change Working Group works to incorporate deep sea considerations of the deep sea into climate policy, sending representatives to the COP, the climate negotiations, producing policy briefs for the delegates, contributing to the Intergovernmental Panel on Climate Change. For example, in the recent special report on oceans and cryosphere, we managed to get 4 different kinds of deep sea ecosystems represented in this burning ember risk diagram that tells us the dangers of different amounts of climate change. The group is working on mainstreaming climate into environmental management, into the designation of protected areas, and the group is just starting to look at the effects of climate remediation and geoengineering on the deep sea. So it's formed a new subgroup to do that. There is a working group focused on this new treaty I mentioned, Biodiversity Beyond National Jurisdiction, that's being negotiated. This group produces policy briefs. They offer critique on the 4 areas of this treaty, which include area-based management tools and MPAs, impact assessments, capacity building and technology, and sharing benefits from marine genetic resources. And this is all for enhancing conservation of biodiversity in international waters. And the Marine Genetic Resources Working Group in DOSI is very active in holding workshops and producing briefs and contributing to the BBNJ Treaty, and also bringing over information from the Convention on Biological Diversity. Many of you may have heard of the Decade for Ocean Sciences for Sustainable Development. DOSI has a working group focused on this and has developed the Challenger 150 program to characterize the whole deep ocean ecologically, and in particular to focus on the less studied regions in the Southern Hemisphere, and largely in the Southern Hemisphere, but through the whole ocean, and to systematically characterize and build understanding, and to build capacity in developing countries, allowing them to understand their deep sea. There's a new technologies working group that focuses on technologies for environmental impact assessment. and developing standards and open access manuals for use by extraction companies. And the newest working group, just getting started, is on pollution and debris, designed to improve public understanding and promote research into debris in the deep sea and pollution in the deep sea, to advocate for the consideration of pollution and debris science and provide expert opinion where needed. So to close, I'd like to just say that to have deep ocean sustainability will require improved science policy interface. And this means doing more deep sea science, having more deep sea scientists, and developing the pathways whereby the scientists can communicate with the many different policymakers that have influence over the deep sea. I think we face, as a society, very tough decisions going forward about how to juggle the needs of the environment, the society, and our economies. And these aren't easy. We have to decide, do we want to mine the deep sea? I should mention there has been no mining to date, but we are certainly on the verge of this. How much of our deep sea fish do we want to take? Do we really need oil and gas from the deep sea at this point in time, given climate change? And I'd like to leave you with this quote from Isaac Asimov, a science fiction writer. No sensible decision can be made any longer without taking into account not the world as it is, but the world as it will be. And I will just say that we need scientists to tell us what this world will be like so that we can make informed decisions. And with that, I'd like to thank you for listening, and I would be happy to answer any questions.
Thank you. Great, Lisa. Great. Thank you for having spoken for around an hour. Great. Just put on my,
Is anybody still there?
Yes, all are there. All are.
Yes, all are there. All are still there. All are were actively listening to you. Very interesting. And you have taken us through the ocean, right from its bottom to the Deep Ocean Stewardship Program. We have first. Let me just come to a few questions which has been raised in the chat box. So we'll just answer those. Then we some of them we could interact. So the first question has come from the former chief scientist of the National Institute of Oceanography, India. He's Dr. Nagendra Nath Bingum. I think Nagendra Nath is online. Would you like to ask, or I will ask? Yes, he's online.
Can I speak?
Yes, please, sir. Please speak.
Can you hear me?
Yes, we can hear you very well. Please come online. Please speak. Yes.
Good evening, Dr. Lisa Levin. We met before in Hartfield, in Portsmouth. So this is regarding the example we cite to show that the disturbance effects are still seen after 20 years. That's mainly we show the DISCOL experiment results. But then we also have, other experiments which have taken place all over the world. And then the restoration was much quicker. So do we really take DISCOL as an example of the deep sea mining which is going to take place? Or the suction devices, which are usually, all the designs now are based on suction devices. The effect is different from the ploughing effect of DISCOL.
Well, I'm less familiar with the suction. I mean, I believe that how much of the sediment is removed with the suction? Yeah. And where is the recovery rapid? Is it rapid in abyssal plains?
Yeah, I'm talking about abyssal plains and manganese nodule experiments. Rapid is 3 to 4 years.
Yeah. Are you talking about the Indian study
Yes.
zone?
Yeah.
I mean, I looked at the impact assessment and I don't remember the details, but there was enough variability that I think it's questionable that there was recovery.
No, no, the numbers are there and the biodiversity is there, so the restoration has taken place in 3 to 4 years. Yeah. So my question is, why do we always take Discol as an example? Discol is very harsh experiment. Very harsh experiment it is. It's not similar to what actually is being devised, the mining devices.
I mean, Discol didn't penetrate the sediment very deeply.
Yes, that's what the ploughing device. It was quite deep. It was. So the marks are still seen because they have plowed the area like a farm.
Yeah. And you have extraction equipment that will not leave any imprint on the sediment?
No, it's not as severe as the Discol.
Yeah, I mean, Discol, because so much of the attention has been on the Clarion-Clipperton zone, the Discol is in the Pacific, right? And isn't it?
Yes.
And so that's the closest analogy. I haven't seen any test mining yet in the Clarion-Clipperton zone, but they're getting ready to do it this year, I think. The testing experiments.
But there were experiments in Clarion-Clipperton zone by Japanese, and then the Russians, and then the IOC. So there were 3 more experiments in the Clarion-Clipperton zone, and the restoration was entirely different compared to the Discol.
I have not seen those reports. Have they published that?
Yes. There are many publications in the Ocean Mining Symposium.
Okay. I haven't seen them, so please send them.
Okay. So I just want to ask you, as you are, of course, you are well known, in the deep sea marine biology, and then you're, championing the cause of the deep ocean sustainability. But can you really say whether, mining will ever take place?
Can I? I definitely cannot say. I'm guessing it will. I mean,
but then
that's the way people are, and
that's one commercial activity. One commercial activity before even a nodule is picked up for a mining. So a lot of environmental concerns are raised. So do you really see that the mining will ever take place?
I honestly don't know, because if you asked me in 1975, I would have said we were right on the verge, and then it stopped for 20, 30 years. Before people got interested again. It seems like a lot of it is subject to the economic situation and the value of the metals. But I also think that many people are questioning whether it is necessary to provide what we need, and whether society has to invade what's more or less one of the most pristine environment, types of environment, or whether the resources can be obtained from land. And after meeting with land miners, I'm learning that many of the damaging features of land mines are now being mitigated with new technologies as well. So, it's a big, I don't want to, hold this debate with you over here and dominate this conversation. It's definitely a big societal decision, and there are people on both sides of that, right?
Because
I have one question, Dr. Bhujanandan. Can I ask
a
second question?
Please. Yeah, you can continue. Yeah, I know. Because what actually why you raise the point is very, very pertinent, because this Discol is because we are going to have the new already the deep ocean policy for mining, especially on mining from the Indian context, the Ministry of Earth Sciences, and large budget has already been earmarked for this. And one of the priority areas is deep ocean mining in the Indian Ocean. So that is very pertinent. Please go ahead with the next question.
Yeah, and this is regarding the, you have shown a plethora of life forms in the deep sea, which actually I'm aware of. The places like the hydrothermal vent systems, or in the seamoon systems, are in the, the coal seep systems, for example, in the margin areas. But then do you really equate the abyssal plains, which are nodule bearing areas, equate with the rainforest, which you said? Can we really call the nodule bearing, which are very poor in the, benthic biota?
Well, I am only really familiar with the diversity in the Clarion-Clipperton zone, and the baseline studies being done by the mining contractors have revealed an amazing array of diversity. It's just so much more diverse than anybody ever thought. So I wouldn't say they're species poor. I cannot speak to the Indian Ocean nodule area, but I would guess if you look at the diversity of small taxa that they also would be very diverse.
Yeah, ma'am, what I mean to say is the diversity is there, but the numbers, the sheer numbers cannot be comparable to the rainforest. The numbers, even in Clarion-Clipperton zone, in the nodule bearing area, you may find, each of the expedition, you may find a new species, but the numbers are not very as much as what you see in the hydrothermal systems. So can we really compare them with the rainforest? Sorry. Yeah.
The biomass, yes, the biomass is low because these are very low productivity regions.
Right. Yep. So that's good. Okay. So I'm through, Professor Nambiar. I have more questions.
Yeah. Thank you, Dr. Nagendra. Nice, excellent. It was nice. It was nice for your mind and your thinking. Nice. And next we have a question from Jonah. She's from Poland. She's one of our MSc marine biology students. She has a very simple question. She has asked, you have mentioned about the metabolites and drugs that can be found in the deep oceans. Definitely. I was wondering how much of these have been discovered. She wants to know, throw some light on your knowledge or information on that. What makes scientists think that this particular organism might have such a substance that may work for this way? Or just every metabolite or drug in a newly discovered organism is being reinvestigated, hoping that it may have such a use?
I believe the shallow water taxa have been the guide. So sponges, for example, have been the source of many interesting metabolites in shallow water. So because sponges are so common in the deep sea, that has caused those people studying genetic resources to go look at the sponges. The same is true for bryozoans and microbes, of course. There are certain groups of microbes that are known, Salinospora and others, to have interesting compounds. And so they go looking for those specific compounds.
Yeah, she's learning. So she's just the basic question. Now, there's a question from Suman Malik. Suman is here online. Yes, this is just but a simple why. It's just already, I mean, it's nothing much to do with here, but it has raised a question why polymetallic nodules are considered as important in minerals. That's just a general question. It's different.
Sure. I mean, they're rich in cobalt, manganese, copper, zinc, I think. The cobalt is of interest because it is used in electric car batteries and I think a variety of other technologies, and the belief is it's in short supply. So the nodules are of interest because there are multiple minerals that can be harvested in the same nodule, right? The argument is that they can be taken more effectively because there's no overburden. In other words, they're sitting on the surface of the mud, as you saw in the pictures. You don't have to excavate to get them. So this, and there's a lot of them. There's vast areas that extend for thousands of kilometers in some cases. And so they've been of interest since the 1960s and 70s, I believe, for mining.
Okay, ma'am, one thing I need to know means how these nodules are formed, means about their formation.
How are they formed? Well, they take, I should have mentioned this, they can take millions of years to grow. You know, they grow very, very slowly. They're precipitated at the seafloor, I believe sometimes with the help of microbes,
Okay.
but they are very slow. So it's a non-renewable resource, effectively. Once you take them, they're gone.
Okay.
Okay,
Thank
now, thank you, Malik. We come to another question from our own students. This is Abhijit wants to know about the Atlantic Meridional Overturnal Circulation AMOC. I think in your listen, in your beginning slide, you said that you informed that there is a recent publication. Yeah, he was referring to a recent publication which claimed that the AMOC is at its weakest in almost a millennium. So the authors predict, based on models, that it can weaken up to 45% by the end of the century if global heating continues. So what's your suggestion?
Yeah,
on this?
this is more or less, I mean, I'm a benthic ecologist. This is more or less out of my area of expertise, but
Yes.
if it does weaken, it is certain to change the climates of North America, of Europe, of, possibly through teleconnection of the entire planet. If you ever saw the movie The Day After Tomorrow, you could get some idea of what could happen.
Nice.
I cannot speak to the
yeah.
evidence for this now.
Yeah. Abhijit, anything you want to like to add? Abhijit, anything? Abhijit, okay, nice. There's another question. No, Abhijit was research scholar of our department. Yeah, sorry. Okay, Meghna, there is another student from Meghna, Deepak. She has asked, Madam, there are many agencies who are working for ocean conservation, but then there is a rapid diversity loss in the marine ecosystem. How we humans, especially those who are interested in ocean studies and research, conserve the oceans more faster the way? That is like your DOSI, also for the exploration of the ocean studies, many modes of transportation facilities are used. Will all these factors disturb the marine ecosystem? Yeah, it's a simple question. Yeah, but it's still your mind.
Yeah, I mean, I'm not sure there's a fast way to do it, but I believe there's a generational way to do it by educating the youth of today to what is happening and how it's happening and how our lifestyles affect the ocean, both through climate change and through overfishing and for the other things we do in the ocean, and why it's important to conserve. I believe that we could create a next generation of people that firmly believe in taking care of the ocean. So education is a really important part of the solution. But there are some things that we can stop doing. For example, we could stop fishing deep sea fish in international waters without affecting the food supply of the planet. We are basically subsidizing those fisheries anyway. And when we fish deep sea fish like on seamounts, it's often like serial mining. Once you've removed the populations, they just grow so slowly, they don't grow back. So there are certain things we can do. We can establish marine protected areas. Some will debate about how effective they will be. They won't necessarily combat climate change, but they can reduce other forms of damage. But then we have to recognize there's other things we're doing in the way of pollution that are much more diffuse. They're not so place-based, and so we can't fix them with a marine protected area, but we can change our use of single-use plastics. I mean, there's so many different ways we can affect things with our lifestyle, with what we choose to eat, what we choose to drive, or how we move ourselves around and so on. So I think nothing, if you're looking for a really fast solution, I don't know that there is one, but I think it's a mindset that needs to come to society. to change the
Thank
mindset.
Thank you. Thank you. Very nice. I think we don't have any more questions in the chat box, but how about Arshia Badra? Is she online? Arshia Badra is online, or a team is online. Anybody from the group? I don't know whether. Yes, please. Why don't you come online and share your thoughts with our global leader of the DOSI program, especially with the DOSI. Yeah, why don't you speak?
Inviting me. And I just wanted to, first of all, thank you all for doing this at this platform, because I think my generation is a very young generation, and we are the ones who are looking at this change for the future. But we often sit and wonder on the other side, and this is what I asked a lot of my seniors, that for a child who belongs to the age group of 12 to 15, how can we be a part of this change? Because we only see devastation, and we know we are helpless. Education is still limited because there's a lot of time before we actually get to that level where we can chemically engineer a change or physically see one happening. So what do we do to protect and be a part of this change is my question to all the people who are here enriching us with so many new thoughts.
Nice, Badra. Very nice. Lisa, you have any...
Well, it's a tough one, but I do have to say that I have seen people in this age group at the United Nations. There is a youth constituency, and I've forgotten whether it's Youngo or the name of it, but there is a way to have a voice and actually be represented and speak in front of policymakers and show and say what you think. I know Greta Thunberg was at the last climate meeting that I attended to, the last COP, and she got a voice and had an amazing, number of followers. You probably know who she is. And I think I am not an expert in how to elevate the voices of youth, but I think there are ways, and certainly social media is one vehicle also.
Thanks for that. Also, I think that the legislations that we currently have in the country, especially with respect to India, because we are, a lot of us belong here and we know the kind of state we're in. There is a huge bridging of gaps that needs to happen, because I think we are still not at the level where legislationally we are protecting, what we can. Our legislations, for example, are very driven towards looking at livelihood of people. They're very driven towards a political vote bank. They're very driven towards protecting only a certain aspect with relation to the oceans, what they have on people. But we are not looking at the ocean itself. So a lot of the legislation, including there was one in 1992, I think, from Orissa, which was aiming at protecting marine conservation. But when I read the legislations, they're not really looking at how to protect life in the ocean. They're looking more or less at protecting people who depend on this life. So I think when I look at the international part of it and the Indian part of it, a lot of these legislations are not yet in the situation where we can protect life around and life inside the ocean. The conservation that we are talking about is conservation of people. I wonder if you agree with me there, and if legislation is also a medium through which this change can be effected.
Well, I do agree with you. You're right. The focus of most policies are to benefit people. They have a very anthropocentric way of looking at the world, but I think that, science is helping to demonstrate that the well-being of people is dependent on the health of the planet, not just people independent of the rest of nature. I mean, there is a movement called the Rights of Nature that is arguing that living species should have their own rights independent of people, but I do think that sentiment about protecting people is not going to go away. I think what people have to realize is we rely on the ocean for keeping the planet livable. Without the ocean, we would be so much warmer from climate change than we are now. We would have so much more of carbon dioxide in the atmosphere and so much more heat that we wouldn't even be able to live on this planet. So we need the ocean. We need it to be healthy. We need it to function and sequester carbon and regenerate nutrients, to have fish to eat. I mean, we need it to be healthy. So I think part of the strategy is to really convince people that to maintain the well-being of the human race, we need to maintain all the species and the diversity of species on the planet and keep them functioning the way they're supposed to be.
Thank you. I think always listening to you, I really feel encouraged, but then there's this feeling that, you know, somewhere down the line, I think education is a slower process than just you know, figuring out a scientific solution for conservation. So my appeal actually to this group, because I know that I'm the youngest here probably, my appeal to all of you is that if you can find solutions which may go hand in hand with, you know, our education and help us implement what you think, because you have the know-how and we might have the spirit. So it's a good combination to sort of match the two and see where we could go. Because I think just waiting for education and the next generation to inherit the change may actually be quite late. But nevertheless, thank you so much for having me being able to ask.
Nice, very nice, Arshia Bhadra.
Is this Arshia talking? You should tell them how old you are. I don't think
12 years. She was just.
I'm 12 years old. That's right.
Yeah, you study, which school you study, Arshia?
I'm in Nada school in India. No.
Oh, Delhi. You are at Delhi. Okay, yeah, nice. Yeah, very nice, Arshia Bhadra. Nice of Lisa to have channelized her to come to this this webinar, also to all of us to have you hearing in this talk, in this webinar. It's really great.
The honor is actually mine. I was very inspired by Professor Levins with a small interview that we did for the United Nations. And I'm really reading with the inspiration. So thank you so much for having me here. It really means a lot.
Thank you. Nice. Really keep it up, and it really inspires all marine biologists, not only as scientists, also as thinkers, also as socializers, all who are working for the oceans and also for the deep oceans. I have just one query, Professor. That is, how about this DOSI? DOSI, how far India can be a signatory to the DOSI, and how much all of us marine biologists in India can get our foot onto this DOSI, and you will be our connector or a link to the DOSI. How far?
If I knew how to write in the chat, I would put the website. Anybody can sign up. It's open.
Yes. Yeah, please.
How do I do it?
You can do it in the chat box. There's a chat box on the right side. Yeah, or you can, just on the chat. There's a chat on the right side. So you can just put it there. All who are interested.
That's the web address, and there's a place.
Yes, that's it. Fine.
If you sign up, you get a weekly newsletter with information about deep ocean activities and papers and webinars and meetings. And then if you sign up for a working group, and I just described all 10 working groups, you know, that's where all the action happens, and that's where you can participate with the group. You can attend. The groups have started with COVID having online meetings to make plans, and then they will critique documents and regulations and set up delegations to visit when the UN meetings are held, and we get observer status for some of these meetings and can speak. to the delegates and in the plenaries. So I would encourage anybody who has an interest in engaging in bringing the science to policy to join DOSI and learn. You can watch for a while and learn how it's done, but then don't be afraid to speak up and volunteer to participate.
Great, excellent. I'm part of this for last several years of the DOSI, since right from our relationship with Lisa and Dave. I'm so privileged, and I think as rightly pointed out by Professor, all of you can just get to Google to this website and be part of the DOSI. I think as rightly pointed out, based on your interest, you can get into the corresponding areas. Thank you all. And any more questions from our distinguished faculties? Anything, any questions, any queries? Yes, Dr. Priyaja, please.
Madam, I would like to just know about the symbiotic relationship you were explaining with the methane oxidizing bacteria and the polychaetes. Can you just explain that symbiotic relationship?
I'm not hearing well. Sorry.
Symbiotic relationship of polychaetes in the methane seeps with bacteria and the polychaetes.
What is the question about them?
Yeah, what is the kind of symbiotic relations? Could you just elaborate on that?
Sure. Well, what we discovered is that these worms, which are amazing because their feeding apparatus is bigger than the body of the worm in some cases. The bacteria are living on the tentacles and in the tissues, so they're basically farmed. They're oxidizing methane, and then the fixed carbon from that oxidation is translocated to the worm, and the isotope signatures of the worms also tell us that they're very, very light carb delta C13 values that tell us that those worms are getting their carbon from methane. And they're getting it from the water, right? The methane from the seep, these worms live around the edges of the seeps, but the methane is moving off the seep and they're able to use that as an energy source. And these are worms that still have a digestive system. And everybody thinks these types of worms are always filter feeders or suspension feeders, but these are in fact living chemoautotrophically.
Okay, are these bacterial strains different from the normal strains found in these vents? Normal methane oxidizing bacteria?
Yeah, they're unique groups. In fact, they're different on the sabellids and the serpulids. So the two different groups of polychaetes have different types of bacteria, but they are, I believe, they're in the same groups as other aerobic methane oxidizing bacteria that might live even free living at vents.
Okay, that's quite interesting. So
but they're unique species, of microbes.
Okay, thank you so much, ma'am, for taking us to the wonderful world of deep ocean. Thank you.
You're welcome.
Thank you. Anybody else? Shall we?
Can I ask Vijay Nandan?
Yes.
Can I ask one question?
Nagendra Saab, please ask.
Okay. Yeah. Professor Lin and Lisa Levin, this regarding the biota, which is associated with the abyssal sediments, and the biota associated with the manganese nodules in their metabolism. The species, they are different on the nodules and compared to the substratum of abyssal sediments. What do they really take? Are any nutritive values the manganese nodules have for these biota which are living on the manganese nodules?
I do not know because I don't work on them. We have a new project. We're actually looking at the animals living on ferromanganese crusts and phosphorites, and I'm working with a natural products chemist to try to answer the question you just asked, so that we're trying to understand how the animals are linked to the microbes, and the microbes are very specific to those mineral substrates, but I cannot answer that question for the nodules. I mean, the animals certainly need the hard substrate, but the real question is, do they also need some aspect of the polymetallic ferromanganese structure? And do you know the answer to that?
The carbon is very poor in manganese nodules, so I don't know, the microbes, there are microbes which are actually oxidizing bacteria. You have microbes, manganese out, but then do they really make a difference to the biota? I'm not very sure.
I think they do. There's Andrew Sweetman has been doing research in the Clarion-Clipperton zone, and it has actually been shown there's carbon fixation going on in those abyssal depths. I don't know the amount and whether it's enough to feed the animals, all of the animals, but it's been underestimated in the past. So he argued that some of the sediment disturbance would reduce the amount of carbon fixation. But you're right, they're very low carbon systems. Everything grows very slowly. And I think we're still discovering how animals make a living down there, to be honest.
Yeah, thank you.
Yes, thank you, Nagendra Sab. Very nice. Thank you. I think we'll be able to wind up. I think it's time is around 11:30 there.
It's only 10:15 p.m.
Oh, nice, 10:15. So your time is up in the bed for the bed.
Pretty soon.
Yes, we didn't take much of your time. Very nice, Professor Lisa, Madam. Thank you for joining and accepting our invitation. A great thank you from each of us who have gathered here from India and other parts of the world. Of course, all delegates, even from not only from CUSAT, from outside, Dr. Nagendra and other scientists from outside. Also thank my fellow colleagues of the department, Dr. Priyaja, Dr. Latika, Dr. Padmakumar, Dr. Swapna, Dr. Hatha, Dr. Anikuti, all my friends and my dear researchers and students. I think it was a very imbibing and inspiring lecture for all of us to move forward, especially in these dying moments of COVID. I think we are almost over the COVID now. I think, and as you rightly said, I'll be using the honorarium as you suggested for the COVID relief in India. That I'll be sharing a part of it for the COVID. Yes, that I'll suggest, because as you rightly told, Madam, we'll do it. Thank you so much, and we will join for another meeting at your convenience. Anyway, finding a time, especially different regions, is great, and you have accepted it. Thank you. On behalf of all in CUSAT Department of Marine Biology and of all Indians, we thank you so much. Convey our regards to
for the opportunity to speak with you.
Thank you. Thank you.
Bye.
Thank you.
Good night, everybody.
Good night. Good night. Bye.
Good morning and good night.
Good night. Good night.
Thank you.
Thank you.